gonna cover this one especially. So I know it has been like a week ago since we were talking about the work. So let's do a little bit of refresh. If you guys remember from last week on Tuesday, we started to lay out how we calculate work on rigid on particles. Okay. So the general rule of work, and we said that the symbol U is the work like from point 1 to point 2, like if I have a body, this body is here, and a bunch of forces acted in this body to move it from point 1 to point 2. Let's say an external force F. Okay, we are talking about chapter 14, work and energy. Okay, so a bunch of forces acting in this body. This body needs to overcome the friction, needs to overcome a strain, need to overcome a weight to get to point 2. So there's a bunch of different forces that we need to understand how to calculate the work for. And the general rule is the integration from position 1 to position 2 to the force dot product of dr, and we said that we can make this from S1 to S2, and the mathematical definition of the dot product is the force multiplied by the displacement multiplied by the angle between the force and displacement. Like for example, if the body is moving, this is S, and this is the force, and this is the angle between the force and displacement. So if you multiply the F vector by the S vector dot product, this is going to be Fs cosine theta. So this is F cosine theta multiplied by ds. If theta is constant, if it's constant, I can take them out and then I can integrate ds. Because ds, sometimes this path is not linear, sometimes it's curved, so I need to integrate over the path. Okay, so this is the general rule of work. Just doing a revision. All this was done last Tuesday. And we applied the same concept to the weight. So if we are calculating the work that's coming from a weight, and we said that this is the integration of negative W dy from y1 to y2. Why this is negative? We said if we have our bodies here and it's coming down, always y is going up, but our weight is going down. So that's why the force is always negative. And y is integrated, depends on the body location. If my body is going up from point 1 to point 2, is that a positive work or a negative work? My body is going from point 1 to point 2. Like I have my water bottle, I need to move it from this position 1 to position 2. Am I exerting positive work or negative work? Negative. Why negative? Because I have to put some work on this to move it, but I don't have to put any work to keep it goes down. So it's the water bottle is exerting positive work to go down, and that makes sense. Why? Because the general rule is going to be negative W y2 minus y1. If y2, the final position, like let's say this is 1 and this is 2. y2 is bigger than y1. So this is going to be positive, and I have this as negative, so it's going to be negative work. But if this is 1 and this is 2, so y2 is less than y1. So this is going to be negative, and this is going to be negative. So the total amount of work is going to be positive, okay? So basically, if you have weight and this weight is going up, so it's negative work. If it's going down, it's positive work. Okay, so this is the work that comes from the weight. Let's put it in a parentheses and let's say weight. And then we have U1 from 2 for a spring. Let's talk about the spring a little bit. So we said that the spring is the integration of the force multiplied by the dot product by the position. And the force in the spring, we call it Fs. And then here we have ds, and from S1 to S2. Okay? So Fs, as we agreed last time, is K multiplied by S. K and S is the compression or the elongation inside the spring. So this after integration from S1, and actually Fs is always negative. Why? We said last time, if this is my spring, okay, and this is my body, and my body is going this way, always F spring is in the other direction, so it's negative. If the spring you are pull it this way, so the F spring is on the other direction, you compress it and you bring your body here, so you put forces this way, the spring is going on the other direction. So the spring force is always in the opposite direction of the applied force.
The spring down?
Down, move this, the maximum that can get stuck. I will try to avoid that. So let's go here. U1, 2 of the spring is the integration from S1 to S2, Fs ds, and this is going to be the integration from S, and this is Fs is going to be negative Ks ds, and once we've done this, it's going to be negative 1 over 2 K S2 squared minus S1 squared. This is not new stuff. We have done this last Tuesday. But I have a very, I was thinking about this morning, and there's a little bit tricky thing that can happen here. Okay, let's say that we have a spring with this length. Let's say the spring length is 5 meters, okay? Then the spring starts from compressed length 3 meters. So we have our body here. So this is position 1. And this is 3 meters. The final position is something this way. And it's 7 meters. If I ask you to calculate the work done by the spring from position 1 to position 2, like the spring was in this position, and you bring it to this position, so you are going to substitute in this equation, let's say U1, 2, negative 1 over 5, K, S2 is going to be, for example, 7 squared minus 3 squared. Okay, so this is how the rule look like. But let's map this out, how it's gonna be. Like, if I draw the relationship between S and Fs, it's gonna be something like this, right? This is the relationship. And this is the final S. Let's say that this is 7 meters, and it started at 3 meters, but actually the 3 meters, like the compression, it's something here. It's in the negative side, like the S, the final S. Let's say this is 2 compression, and this is 2 tension. So it's something like here. So you have a bunch of work here at the negative side and bunch of work at the positive side. Okay? So that's what the spring did. It came from here to the 0, and then a bunch of work until it gets to 2, and another bunch of work in the positive direction. So you have 2, let's make it equal, so something like this. But my rule here is a square, so it takes into account all of that, okay? So that's why this is our rule. So don't worry about the signs, you just substitute in the final S and the initial S. If I told you, like the exam, that S unrestricted, so S1 means it's equal to, if the spring started at unrestricted length, 0, so S1 is 0, and then rigid, like for example 2 meters, so like it was extended by 2 meters, so this is going to be 2, or was compressed by 2 meters, this is going to be 2. So when I say unrestricted, that means something. Like when I say that the spring started at unrestricted length, so that means that at rest, S1 is equal to 0.
So if it's stretched or compressed, it exerts the same force, just in the opposite direction?
Yes. Okay, right, so this is all the words that we need. And then we move to a new concept. This concept is called work and energy. Like if you need to move this body from here to here, this body has a kinetic energy, we call it like T1, and a kinetic energy here T2. So to move from here to here, you put some work to get to this level of energy. How we proved this? We proved it last time, that since this is Newton's second law, we know that A is equal to V dV ds. Then we got ds here, so we have F ds is equal to mv dV. Then we integrated both sides from S1 to S2, and here from V1 to V2. This actually is the work forced by displacement. So the work from 1 to 2 is equal to half mv squared from V1 to V2, and this is actually equal to half mv2 squared minus half mv1 squared. That's all the rules that we have in this chapter. Okay, so this minus this. Or we can write it, this is kinetic energy at position 2 minus kinetic energy at position 1. We can rewrite this equation by sending this to the left-hand side. So T1 plus the work from 1 to 2 is equal to T2, the kinetic energy at position 1, plus the work from 1 to 2 is gonna give you the kinetic energy at position 2, and then we solve the problem on this. Does anybody have any question? All this from last Tuesday. We just put it out there in like 12 minutes. Okay, so this is all the rules that we need. The general rule of work, the work done by the weight, the work done by the spring, and the work energy relationship. So here we have T1, and this is the work. By the way, this is kinetic energy, so that's only something related to the velocity, half mv squared, okay? And this is all the work done by all the other forces, all right? Okay, does anybody have any question? Yeah.
For S1, if it starts on stretch, wouldn't it be 5 and not 0?
This one?
Yeah, if it starts unstretched, would it be 5?
No, yeah, it will be 5, but right here I'm saying it's 3.
Okay.
Okay, so this is the starting position. So if it starts at a compression position, so if S is equal to 3 meters, so we are gonna start with 3, the length of the spring. And this is the final length of the spring.
No, because you said if it starts unstretched, you said it was going to be
If
0.
it's unstretched, it's gonna be 0. Like if I don't give you this, and I told you the unstretched length is 5 meters, and then we hold the spring and it extended 2 meters, so it's gonna be 7. So it's, you are gonna say it's a 7. Interesting. Oh yeah, you are asking what number that I'm gonna put here?
Yeah.
0 or 5? No, it's gonna be 5.
Oh, okay.
Because this is the length. Okay, so you are gonna put the lengths as 5 meters and 7 meters.
Okay.
All right, yeah. The spring force, no, this is the work. The spring force Fs is equal to K multiplied by S. This is the spring force.
Yeah, I'm just saying because the S is usually S minus S1, or S0, sorry. So is that relationship?
You mean like the compression? There's different ways that you can calculate the work, but right now we are making it arbitrary, like it's with respect to a datum.
Okay.
So my datum is like, for example, it's this way, like it says like it's from here, so it's from 3 meters to 7 meters, so it's a 7 minus 3, okay? But if you wanted to divide your motion, like if you wanted really to do analytical analysis on how the work is done, you can divide the spring. Like let's say my spring was compressed like this, and this is 0, okay? And this is the unstretched length, and let's say it's a 5 meters, like this one. Then it was compressed, and it came here, and it becomes 3. So you wanna do the first piece, then you compress it this way, okay? So you got something like this way, so you can calculate this work the first piece, this one, the negative bar. And it's gonna be positive, okay? Because this is Fs and this is S, so you have S is negative, and this is K multiplied by S, so this negative is gonna be positive, so it's gonna be a work exerted by the body. And then you need to do like the other part, and then you get the work that you have done it from here to here. Okay? Or you do the integration from S1 to S2. Okay? Alright, so here when I mean S1 to S2, like you have, for example, let's say that you have and something like this. So the spring doesn't depend on the mass of the particle. All the energy or all the work done by this spring depends on the elongation of the spring. So you need to find the S1 length of the spring and the final S of the spring. Okay, so that's what we care about. So how it was and how and the final end. We are gonna come to the energy and explain it more. But does anyone have any questions so far in this part?
What is the T to the right? What does that stand for?
T1. This is the kinetic energy. Okay, and kinetic energy is always half mv squared. If we are saying T1, so it's half mv1 squared. Alright, so this rule can be changed to a different rule. Let's discuss right now something that's called conservative forces. What is the difference between conservative forces and non-conservative forces? So, so the conservative forces that we have here, number one, is the weight force. And number two is the spring force. These are the two conservative forces that we have. What does it mean, conservative force? Conservative force means that it doesn't depend on the mass that the body's gonna take. How? Like, for example, if we have a weight, this is the ground, okay? And this body is gonna come to the ground somehow. Let's put the ground a little bit higher. Alright? This body is gonna fall. Let's say this body is gonna fall this way, or actually it's gonna take a bass like this, or a bass like this. The energy or the energy that this body take from here to here doesn't depend on the bass. Like if it goes down right away, or if it goes this way or goes this way, it still depends on the height. Okay, when we say the energy or the work done by this way, it's W y2 minus y1. It's just the vertical level. If my body fold vertically like this, or make a curve, or was a projectile, it doesn't make any difference. It's gonna be the same amount of work. So we call this a conservative, and it's equal to, as a work actually, it's not gonna work. And that will take us to what's called potential energy. So we say, if my body's up, we say that it has a potential energy V, and this V is the weight of the body multiplied by the height from the datum, and let's say it's Y. And actually it's the same like the work, WY. But it's gonna be positive, and I'm gonna tell you why. If this is my datum, I'm gonna say this is the ground. And if my body, like this, then I'm not gonna make it fall again. So this then is here, and I'm gonna let it fold so it has a potential energy to do some work, okay? So it's gonna go down. So it has a positive potential energy. But if my body's here, it has negative potential energy, because if you want to bring it to the datum, you have to exert work to bring it back to the datum. So let's say that my body is at a height y, so this is going to be y, and also this is going to be y. So this is the potential energy V is equal to negative W y, okay? We say VW, I think. This is VW, and VW, okay? So that's why we call this is a conservative force, okay? Why? Because it doesn't depend on the mass that this body's gonna take. Whatever this body is gonna move, like let's say this body's gonna move like this, and then it's gonna move something like this, and it came here, and then make it this way. It's still, the potential energy here is negative W multiplied by Y. So if you are gonna solve a problem this way, you have to pick a datum, fixed datum, and you always measure from this datum. Either you make it down, you make it in the half, make it in the middle, whatever you would like. And then if the body is above the datum, it has a positive potential energy. It's below the datum, it has a negative potential energy. That's only for conservative force. Let's see for the spring. Spring is kind of similar. It's also depends on, it doesn't depend on the mass of the particle. It always depends on, like let's say, like something that I wrote here, like let's draw half a circle, and I have a spring here, and I have a body here, and this body is gonna move in this circle. Okay, let's say that my body at some point got here. Okay, so it got this S distance. My spring starts to be something like this. This spring, the force in this spring doesn't depend on the back. It depends on how this spring elongated. Okay, so the spring has what's called elastic potential energy. Okay, so this elastic potential energy is equal to, let's actually right here, Vg or Vw is equal to Wy, positive or negative depends on the elevation from the datum. Same thing, the Ve of the elastic spring is equal to positive half k s squared. Okay, let's say that we have our spring unstretched. It's okay to write here, everyone see?
Yeah.
So this is the unstretched length of a spring. So this is unstretched, and then I stretch this spring a little bit. Then I compress this spring a little bit. Okay, so this is gonna be my datum or unstretched length. Okay, so it always needs a datum, and my datum here is unstretched length, and then here it has S positive, and then here has S negative. So the VE, the potential energy, like let's say I have a body, my body's here, and this body came here, and this body came here. So the energy here is always positive, okay? When we talk energy, there is no negative and positive. The energy is always positive. All right, so the energy that this body has here is equal to V spring or VE, elastic energy, is equal to positive half K S squared. And S is the distance measured from the datum. The datum here is the unstretched length. So this body has an energy based on this distance. If my body's here, the energy is zero, because if I lift my body, it's gonna stay the same. But if I stretch it, so I stored some energy in this spring, once I leave this, all this energy is gonna be released, and this body's gonna go to the datum. Same thing when I raise my body up, and I leave it, so it has a potential energy, and wanna go to the datum, wanna go to where it can come down, okay, like this, right? Same thing, this spring, once you stretch it, it has a lot of elastic energy. Once you leave it, when it goes to where the energy is zero. So it has half Ks squared. Same thing if it's compressed. So the V is gonna be equal to positive 1 over 2K S squared. So it doesn't depend if it's tension or compression, it's always the energy is gonna be positive because energy doesn't have negative value, always positive. So once you leave it, it wanna expand back and goes to the original data, okay? So it's always positive half Ks squared. So these are the only two forces that we call them, that has like a potential energy or elastic energy, or we call them conservative forces or conservative energy. So if we want to write the general rule, I want you to look at this. This is kinetic. What is the summation of the work from 1 to 2? The summation of work from 1 to 2 has everything. Has the work done by external forces, has the work done by the weight, has the work done by the spring, has everything. So you can use this rule and like, don't look at what's happening here. Or we expand this rule to be T1 plus V1 plus the sum of U1 to 2 equal to T2 plus V2. So what is this? This is a rule similar to this one, but we take all the conservative forces that make work from this and convert them to potential energy. So we are saying that the kinetic energy at position 1 plus the potential energy at position 1, and let's like make that you are not seeing this, okay? Just not see this for a little bit. The kinetic energy plus the potential energy at position 1 is equal to the kinetic energy and the potential energy at position 2, okay? So this is the general rule. Like, for example, this body has lots of potential energy, okay? But the kinetic energy is 0 because it starts from rest. So this is 0 and this has value. Once it came down, the potential energy is 0, but it has velocity. So the kinetic energy has value. So the energy is transforming from shape to another, from potential energy to kinetic energy. Once this body is left from rest, where the kinetic energy is 0, it starts to have velocity, and the velocity is getting increased and has an acceleration. The kinetic energy is increasing while the potential energy decreasing, until the potential energy gets to 0, where the kinetic energy is maximum. So that's where the energy is getting transformed from shape to another. You guys understand that? So like if I have a body here, what is the kinetic energy?
0.
0, right? Because it doesn't move, okay? But it has a potential energy, which is mgh, or W multiplied by h, which is this height. As h is getting decreased, so the potential energy is getting decreased. While it's moving and has lots of velocity, so it starts to gain more kinetic energy, okay? So this is, if we are dealing with a system that doesn't have non-conservative forces, like all what we deal with, springs, weight, so there's no other external forces. But let's say that this body is acted on up by like a force. Let's say like you have a rocket, okay? And this rocket is shooting from the ground. So at the ground, potential energy is 0, kinetic energy is 0, right? And then the motor starts. So the motor, like when it starts and pushing forces to the rocket, so this is non-conservative force. Okay, why? Let's start here. We talk about conservative forces. What is the non-conservative forces? The non-conservative forces is the forces that depend on the path. Like you have, for example, your body's here, and you are pushing the force here, and this force is moving with the body. So this force depends on the mass because the work is F multiplied by S. If the S is this way, it's different as the S is this way, it's different as the S is this way. So this force is gonna be more work, less work, less work, less work, because the distance is less, okay? So external forces are always non-conservative forces. So if your problem has non-conservative forces, we have to put another term, which is this term, okay? That's why, like if you put the textbook, you will not find this. You will find two rules. One is T1 plus V1 is equal to T2 V2 if your problem doesn't have non-conservative forces. But if like it's only springs and weights, okay? But if your problem has an external force, you will find that this term exists. So you have to keep it that way. Actually, this rule is almost the same. This one is the same like this one. But what I did here, I take out all the potential energy terms and put them here and put here a bar for the non-conservative forces. Okay?
So, Professor, there's no external work being done, we just take out the sum of the work done once it's here?
Yeah, like if there's no external forces and you are dealing with something that is falling or a spring that is stretching. So all this is gonna be zero.
Okay.
And it's gonna be T1 plus V1 equal to T2 plus V2. So let's I'm gonna put this rule in a form, in an expanded form. Okay. Here's the two important rules in this chapters or formulas. The first one is T1 plus the sum of u from 1 to 2 is equal to T2, and this can be expanded to half mv1 squared plus u1 to u2 and half mv2 squared. Okay. It's called the work energy. Okay, work energy formula. If it's conservative, it's gonna be D1 plus D1 plus the sum from U1 to 2, and let's put it here, unconservative. Okay, equal to T2 plus V2. If we are gonna expand this the same way that we did here, it's gonna be a very, very big rule. It's gonna be half mv1 squared plus v1 can be potential energy coming from weight or spring. Let's write both. So this is gonna be mgh 1 plus half ks1 squared. This is the potential energy that coming from the weight, and this is the potential energy that coming from the spring. If your problem doesn't have a spring, so this is gonna be 0. Plus sum, the work from 1 to 2, unconservative forces, is equal to this is going to be equal to T2, which is half mv2 squared, plus the potential energy that comes from the weight. So it's mgh2 plus the potential energy or the elastic energy in the spring, so which is half ks2 squared. Okay, so what is h1? h1 is the height measured from the datum. Okay, so you will have to have a datum in your problem and you measure the height from. If the height is positive, so it's gonna be positive. If it's negative, it's gonna be negative. Okay? Same thing. S1, it's measured from the datum, and the datum is the unstretched length. Okay, so you're gonna measure S1 and S2. Alright, so this is the general rule of the relationship between work. Doesn't have work, it's all energy, but we have unconservative work coming from the unconservative forces. Okay, so let's solve a problem using this one they are pretty much similar. And this one. How it's a similar? Like imagine with me, if you bring this bar to the other side, so it's gonna be negative mg multiplied by h2 minus h1, which is actually I don't know, I removed it, which is actually the work done by the weight. If you bring this to the other side, and you have half k s2 squared minus s1 squared, which is the work done by the spring. And you can take them and put them here. Okay, so it's almost the same thing, but what we did, we expanded them, position 1 and position 2. Rather than having half k s2 squared minus s1 squared, we send the other one in the other direction, we keep here the other one. Same thing with the weight, mg h2 minus h1 or delta y, we put them in different, so it's almost the same thing. So let's solve the problem and see how it's being done. So what we have here is a system. You have a bar, and this bar has a spring here, and this is spring, the distance from here to here is 6 inches. Okay? And we have a pulley here with a cord, and this cord has a tension force of 50 pounds attached to this pulley, and this pulley has the cord extension all the way down to this cord. Okay, so the problem is saying that pulley C and AB bar form a right triangle. So this is a right triangle, 30 inches, 40 inches. So if this is a start from here, do you guys know what's the length of this
50.
cord? It's gonna be 50 inches, right? 6, 3, 4, 5, 30, 40, 50, okay? All right, and it says that the collar has a weight. This collar has a weight of 30 pounds. It starts at rest from A, so A is at rest. So that means that VA is equal to 0. So use all the information that is given, okay? Slides frictionless, friction-free, up, so no friction, okay? And compress a spring 6 inches. So once it came from point A to point B, this spring is gonna be compressed 6 inches, okay? And the K is 200 pound-feet. To reach to point B, okay? So it's gonna, this is where the spring is unrestricted, because there's no compression, there's nothing. So it starts from here to goes here to point B. So it's not gonna compress it all the way down. It doesn't matter how long is this spring. This is how much is gonna be compressed. So what I'm asking for, what is the velocity of this collar at B? What is V B? Okay. All right. So let's solve this problem. We're gonna solve it using different approaches. Number one. Let's number one using the principle of work and energy. Using the principle of work and energy. Using the principle of work and energy, so this is the principle of work and energy. It doesn't have any conservative forces. We're not going to consider this. It's going to be T1 plus sum of the work from 1 to 2 or from A to B. Let's put it A to B. And let's put 1 as A. So TA, the work from A to B is equal to TB. So let's put this half MVA squared plus the work from A to B is going to be half MVB squared, which is what is required here. We need VB. Okay. Before I start, definitely there is velocity at B. That's what that's what it's asking for. So which is this term. But this term has something special. What is it? Half MVA squared. It's gonna be, it says A is at rest. This body starts at rest here. So VA is equal to 0, so this term is 0. So I'm left out with the work from A to B. What the forces that do work on this body? Spring force, but this is when my body comes here, right? So what other things? We have weight. What else? The constant force B. Okay, but actually it's not constant. Yeah, it's constant B as it's the tension in the rod, but actually what is the part of this force that is making work is like the component of the force, right? And actually the component of the force is changing, right? Why? Because theta is changing. Like imagine this is my bar. I need you to think about this. This is my bar and my body's here, and this is my ball is here, and it's pulling this way. At some point, this is the V, right? When my body comes here, it's gonna be this way. When my body comes here, it's gonna be this way. So theta is keep it changing, and the components that does the work is keep it changing. So theta is constant. I cannot get it out of the integration, right? We agree on this. Just like keep this in mind. So the forces that make work on this body is the weight is going down, okay? But it doesn't matter for now. Like let's keep it. We are gonna use the rules of the work, and then weight, spring, and force speed. Let's talk about conservative and non-conservative. We have three forces that make work: weight, spring, and force speed. Which one is conservative? The weight and the spring are conservative. Which one is unconservative? Is the force speed. Why? Because it is keep it changing. Like it changed with S, so it's not conservative. Okay. So we have three forces. So let's get them one by one. But let's me get the force done by V. Okay. Let's go to the first principle. The work from A to B by the force speed. The integration from S1 to S2 for the force speed ds cosine theta. So let's put F cosine theta right away. As we said, this is going to be F cosine theta ds. If you are asking where this is coming from, in the first lecture we wrote the general rule that the force dot product R is Fs cosine theta. All right, so right now I have F is constant, the force 50, but the theta is not constant. So what should I do? Okay, and also this is theta and this is ds. If theta is the variable, it's either I convert the ds to d theta or I convert theta to s, because I'll not be able to integrate it. This is a variable and ds is here. Like we always know, like I have x dx, I can integrate this because the variable is have the dx with. Like if I have y here, I will not be able to integrate it. I need a function that says y is equal to x squared plus 2x, and I substitute here to do this integration. Same thing I have to do it with theta. So let's find out what we can do about this. Some geometry, okay? So this is, my body is moving from here to here. This is S1 is equal to 0, and this is S2 is equal to 40 inches. But keep attention to the units, okay? Because I'm giving this problem, I'm saying, for example, the K is 200 pound per feet, okay? And so I have feet. And when I use G, like mg, G is 32.2 feet per second square. So everything is gonna be in feet, but all the units here is gonna be in inch. So we need to convert all the inches to feet and make the problem like in feet and second and all of this stuff. Okay. All right, so let's find out how we can calculate the work done by the external force. So I'm gonna write S2, here is 40 inch, 40 over 12, so that we can convert it to feet. And I have my pulley here, and it pulls this way, and this is, let's say for example, at any random position, my body came here, okay? And this is the angle theta. I have, this is constant, 30 inches. So this is 30 over 12. And this is the distance S, okay? Alright, so this is the distance S that my body needs to cut. If my body's here, so all here is the distance S. So let's get cosine theta. Can any of you get cosine theta? It's gonna be equal to, from this geometry. What should I do first? I need to find this length, right? So this length is gonna be, you have this is 30 over 12, and this is S. So it's gonna be S squared plus 30 over 12 squared, right?
Yes.
And then cosine theta is gonna be equal to S over
Square
square root of S squared over 30 over 12 squared. So I find cosine theta as a function of s, so I can do this integration. The integration from s1, which is 0, to s2, which is 40 over 12, and FB, the force is 50, right? Multiplied by cosine theta, which is s over root s squared plus 30 over 12 squared, and this is ds. You do this on your calculator, okay? You don't have to do it by hand. Do you guys know how to do integration with the calculator? Okay, so you start the integration and then put the upper limit, the lower limit, and the upper limit, and use any variable, x, y, b. Once you do this, this is gonna be, maybe you do integration for this part. You find what is the value of this part? This part is gonna be 50 multiplied by 20 over 12, and this is gonna be 83.33 pounds per feet. This is very, very special. Why? This is not a constant force. This is a force that keeps changing with the back. The values keep changing. Why? Because the force, the tension in the cord is constant, 50. But the angle that this cord is making with the back is keep changing, which is theta. So that's why the forces keep changing. That's why I have to keep the cosine theta inside the integration and do the integration and find the work. All right, I find the work of the constant force. I need to find the work of the other forces. Okay, so let me write here, like let's expand, where's the, yeah, this one. Let's expand this one. So I have TA is half mv squared plus the work first done by the weight, we can write it as negative mg multiplied by HAB, h from AN to B, minus the work done by the spring, half K, S2 squared minus S1 squared is gonna be equal to, still we have the work done by the non-conservative force. So right now I did the work by the weight, work by the spring, work by the force P. This is gonna be equal to half mvb squared. All right. This one, we know it's a 0. This one, we just got it. This one, what is needed from the problem. So I'm left out with these two to find out what is the value of these two. So let's find out what is the value of these two. I have the m, the mass. Mg actually is the w, so I can replace mg and put w, which is negative 30, multiplied by h from a to b. Why this is negative? Because this body is going up. Okay? So what is HAB? As I said before, you have this water bottle, you are gonna raise it up, so it's gonna be negative work. If it's going down, it's gonna be positive work. That's why I put this is negative, and I need to find the distance, the height from here up there. So, and that's very easy. How? I need to do some geometry. I give you the angle, it's 30 degrees. I need to find this height. From here to here. If I know that this angle is 30 degrees, and I know that this is 40 inches, so what is this height? 40 cosine or sine?
Sine.
Sine 30, right?
Yeah.
This is something like this. I'm telling you that this is 40 inch, and this is 30 degree. So this is 40 cosine 30, and this is 40 sine 30. So HAB is the vertical height, because I'm only curious about the vertical height that this body is moving, because weight is going down, so I'm only curious on the vertical height. So the vertical height is 40 multiplied by 30, which is this bar. So this is gonna be negative 30 multiplied by 40, but right now this is 40 inches. I'm gonna divide over 12 sine 30. Why? Because I need to convert this to feet. Everything is gonna be feet. let's get to the spring. Minus 1.5, and then we have K. K is given 200 pound-feet. Multiplied by S2 minus S1. Okay, so let's find. S2, this is the unrestricted length, or this where it starts from. So this is S1 for the spring, and this is S2 for the spring, okay? So S1 is 0, and S2 is 6 inches. So you have 6 inches over 12, all square, minus 0 square, plus the force by the unconservative force, the one that we calculated here, plus 83.33 is equal to half the mass. The mass is, I have W. So how can I get the mass from the W? So it's gonna be 30 over 32.2 multiplied by VV squared. So right now I put all the numbers. Okay, focus with me. I have 3 forces is doing work. I have the weight, I have the spring, I have the external force. Right here I showed you how to get the external force because it's non-conservative and it's changing. So I have to do the integration from S equals 0 to S equals 40 over 12. And I showed you how to do the integration. Cosine theta does not function in S. So I need to convert cosine theta to something function in S. I did some geometry, and I found by Pythagorean theory, I found what is the cosine theta is. Theta, and here's S. If you wanna make it from here, this is still theta. This is the initial value of theta, and this is the total S. So S square plus 30 over 12 square is gonna give you this length. So cosine theta is S over the square root. So I substitute it here. I get the work done by the force P, the non-conservative force. So this one is done. I'm left out with the kinetic energy at VA, and it's equal to 0 because it starts at rest, and then the work done by the weight, and then the work done by the spring, and they are always negative. If you look at the rules that I put here, when I started the lecture, it was negative W multiplied by delta Y, negative A S2 S1 squared. And then I substitute with the numbers. Once you are done, do the calculation. You will find VB squared. You will take the square root, and the VB is gonna be 4.23 feet per second. And keep attention to the unit. We need all the unit is in feet. So I need to convert all the inches to feet. Okay, let's solve this problem using different approach. Same problem. I'm gonna solve this problem using this rule.
Professor, how do you get the displacement of the spring?
The displacement of the spring is from here to here, and I said this is 6 inches. So S1 is 0, the one where we start from, the unrestricted length, and S2 measured from the unrestricted length is 6 inches. Okay? Alright, so this problem I'm gonna continue. I'm gonna put number 2 here. Solving using the conservation of energy. This rule is the conservation of energy equation. So let's solve it using this rule. First one, V1, let's say that V1 is the V8 and V2 is the VB. V1 is 0. I need to pick a datum. So I'm gonna pick the datum, let's say here. This is my datum. Okay? So if this is my datum, what is the potential energy at A or at 1? Where it starts?
Potential 0?
0, right?
Yeah.
Why? Because it starts from here and the h from the datum is 0, okay? Somebody will, okay, I'm gonna make the datum here. Make the datum here, it's gonna be the same thing. This is gonna be the h1 and this one is gonna be the h2 and it's gonna give you the same thing. So I make my datum here to make lots of zeros as much as I can. So, okay, let's see, where did I bake the datum here? Yeah, I baked the datum at the same location. And this is gonna be 0 mgh1. Alright, half k s1 squared. Half k s1 squared is 0. Why? Because this is where the spring starts, from the unrestricted length. So the potential energy in the spring is equal to 0. Okay? The work done by the unconservative force, you are going to do the same thing that we have done here. Okay? This is the only thing that is similar. So the work is done by the conservative force is 83.33. Let me write this up so that you guys can write it. And so, 83.33. This is going to be equal half mvb squared. And I'm going to remove m and put 30 half 30 over 32.2 because I need the mass, not the weight. And then mgh2, so plus mg is the weight, so I'm going to put 30 right away. And h2 is this height, right? So this is where my body starts, where the datum is 0. So this is the 0. And then my body goes all the way up until to this point, which is 40 sine 30. So it's going to be, h2 is going to be 40 over 12 sine 30. This is h2 plus half k s2 squared. So half k is going to be 200 multiplied by s2. S2 is 6 inch because this is my unrestricted length, and it was compressed by 6 inches. So this is going to be 6 over 12 squared. Solve this and then find VB. And VB is going to be equal to same thing, 4.23 feet per second. And that's what is the requirement. It is the same thing. Look at the numbers. I have here 30 over multiplied by this part, you will find it here. But it's negative here because the other side is positive. If you want to send it to the other side, it's going to be positive. Same thing as the spring. Negative half multiplied by 206, you can send it to the other side with positive. And then here you have mvb squared as it is. So which one is much simpler? I believe this one, right? Because this one doesn't get you in the confusion, what is positive, what is negative. You just put a datum and you measure it. It's up the datum positive, lower the datum, it's going to be negative. And it's separate. It doesn't get you confused like which one you need to subtract from each one. So it puts all the initial positions and all the final positions. But pick the right datum. That makes your problem easier. Because if you pick the datum here, it's going to have lots of numbers. This is going to have a value and this is going to have a value. We need to make as much zeros as we can. If you can make, sometimes in problems, the datum for the weight can be the same datum for the spring, and we can make all of them equal to 0 as initial position. Okay? All right, does anyone have any questions? All right, so I solved some other problems here, but I'm gonna leave it for you to think about them. I'm gonna end this chapter with one last rule. It's called the power and efficiency. In the textbook, you are gonna find a problem, and I believe I solved this problem here as well. Do you guys remember the spring problem that we solved it in the work and energy? And you have a color is moving up and down. He solved the same problem using the conservation of energy. So in the textbook, when we solved this in chapter 13, he didn't calculate velocity. But if you go back to the notes, I showed you how to calculate velocity. It checked the two numbers, solve this with Newtonian kinetics and also with the work and energy, you will get the same answer. But this one is much simpler. This one is very, very simple. If you go back to the notes, you will find that I did a very, very long integration to get the velocity with Newtonian kinetics. Here, it's just this line, substitute, you are gonna get the velocity V2 or VB. But back then, if you solve it using the Newtonian kinetics, you need to integrate the acceleration to get the velocity, and it has lots of roots, like you need lots of complex integration. So just go back and solve this problem It will be interesting to find, it's not gonna be exactly the same numbers, like it's gonna be 4.4 and the other one is 4.2 or 4.3, maybe because some rounding, but it's almost the same. Okay, so let's finish this chapter. The last part, chapter 14.4, power and efficiency. So, power is the time rate of a change of work. How? So power, time rate of a change is d dt, this is the description of the time rate of a change, work d, work dt. So this is gonna be d dt of the force multiplied by the distance, fs, or let's actually put it in the format of the vector, dr, the dot product of the force multiplied by the position. So if you did this and the force is constant, so this is gonna be f vector multiplied by d dt to the position r, and actually the time rate of a change of the position is, what is the time rate of a change of the position? Velocity. So it's gonna be the force multiplied by the velocity. If both the force and the velocity are in the same direction and you multiply them together, so it's gonna give you the power. And very important notes about the units of the power. So SI units is gonna be, it's work over time. So power is work over time, work over time. Actually, you can write U over T. So it's gonna be joule per second. This is the SI unit, and actually this is equal to what? Okay, joule over second is what? Okay. All right. So if it's American units, US units, it's gonna be feet bound, because this is how the work is, over second. Or we can measure this using the horsepower. The horsepower is 550 feet pound over second. This is equal to 1 horsepower. And if you have a problem that has mixed units between metric and US units, the 1 horsepower is equal to 745.7 meter Newton over second, and meter Newton actually is joule. So keep attention of these units. I'm not sure if it's in the sheet, the equation sheet or not. Okay, so this is for the power. So let's get to the efficiency. So the efficiency, we're gonna say EM, and it's equal to the power. It's the ratio between the power done by a machine to the power done on the machine. How? Like if you have a motor, and this motor has an output power to build something, like let's say a body on a curve or something. Like this is the power out. But you put like a fuel or a gas or something inside this, so it has a power comes in this power in. That is inside the motor. The motor has like something that is rotating or something, so it has in power, but the output power that it can build this body is, we call it B out. And the efficiency of this motor is B out over Bn. The output power from the machine, but over the input power to the machine. And actually it's gonna be given in the problem. Like, for example, we are not mechanical engineers. Mechanical engineers is gonna do this machine and tell us that this is how much input power that this machine needs, okay? But the output, it just depends on the friction, it depends on many things outside. Definitely this number is bigger than 1 or less than 1, the efficiency. It is always less than 1. If it's bigger than 1, so you either like came up with a new theory and you're gonna be a millionaire because you are gonna make your machine has more efficiency more than 100%. So or definitely you have a mathematical error, that's for sure. Okay, so you need to check back, like, okay, I got my powers like at 25, oh my goodness, you need to go back, check what is mathematical error that you have done, and check for this. Okay, let's solve a problem very quick, and maybe I will tell the idea. So I have a motor here or a winch, and I have a log here, or whatever, any body here, and this body is attached to a cord, and I have a frictionless pulley here, and then this cord is attached to the motor, okay? So the winch pulls, this is log, and the weight is, for this log is 800 pounds, and it goes up on a slope, this slope 30 degrees, with a constant velocity. V is equal to 4 feet per second, and it's constant, okay? And the output power from this winch, the B out, is equal to 6 horsepower. So 6 horsepower multiplied by 550, so that we can convert them to feet bound per second, and then you can get it. And what I'm asking for, what is mu K? What is the friction here on this surface? Okay? Well, let's start step by step. If you are given the B out, so we know that B is equal to the force multiplied by the velocity, right? The force vector, which is the tension here in this cord, F, let's say it's tension, T, and dot product, the velocity is 4 feet per second, and definitely it is this way. So T multiplied by 4 cosine theta. The theta between the velocity and the force is 0, so its cosine theta is 1. So if you want to put this, it's going to be F V cosine theta. Okay, as we said, like this is V, this is F, and this is theta. So the dot product of F vector with V vector is going to be F V cosine theta. It happens here that the velocity of this body is in the same direction of the force, so the theta is 0, so this is going to be T multiplied by 4. Okay, so find out the 6 horsepower. The 6 horsepower is going to be 6 multiplied by 550. You will be able to find the tension in this cord. So the tension in this cord is going to be T, it's going to be 6 multiplied by 550 over 4. So this is going to give you a tension of 825 pounds. Is that difficult?
No.
To find the tension in the cord? I give you the power, and the power is equal to the force multiplied the velocity. Give you the power and velocity, you find the tension. This is the very thing. And then you will solve a Newtonian kinetics problem. How? You make a free body diagram. For this body, you have the weight is going down, you have the normal force, you have the friction. This body is going up, so the friction is going down, so you have Fs. What is else? And you have the tension is going up. Okay? So this is the free body diagram. You put some angles, so you know that this angle is 30 degrees. If this angle is 50 degrees, so this angle is 30 degrees. Then all you have to do is to get the sum of Fy is equal to MAY. I'm gonna make a kinetic diagram, so you have this is X, this is Y, and then you solve this problem in Fy direction. You will find that W sine 30 is equal, W sine 30 is going down, so it's negative.
Negative, yeah.
Okay, so I'm gonna put negative, and n is going up, so it's positive, so I have W and n, and all this is equal to 0 because there is no AY. This body definitely moving in the x direction. So n is equal to W sine 30. We'll find out that the n is 692.82. And sum of fx equal to max, y here is 0. And I told you that the velocity is constant. So the acceleration in the x direction is also 0. So what is the forces in the x direction? You have the
Tension
tension,
and friction.
positive, and then you have the F of friction is going to the other way, which is us multiplied by n. And then what else? You have the component of the weight is negative W.
Sine. Sine of the.
Okay, so
We'll
here,
flip it over.
this one is cosine,
Is it sine? No, it's cosine.
and this one W sine
No, it's
30,
sine of
and
30.
all this is
Cosine
equal
of
to
60.
0. Once
Sine of
you
30.
solve this, you'll find that you have t, we just got it. Where? It's here, 825. Then we'll find what is the US is equal to. So US is gonna be equal to 0.61. The last question, it gives you in the problem, here is the, where? Yeah, the B out. It gives you the BN directly in the problem. So BN, it says it's equal to, if the power delivered to the motor is 3,740 feet pound per second. So it's very, very easy. So the efficiency, EM is B out over B end. B out we just calculated, which is 6 multiplied by 550, and then here is the BN, 3,740. Once you do the calculation, you'll find that the efficiency is 88.2%. And actually that's all about the efficiency. I'm giving you the N, I'm giving you the out, and all I'm asking you is to divide them over each other. And this is simple kinetic, Newtonian kinetic problem. I just use the power to get the tension, that's it, okay?
It's very, very simple.
All right, so that's all for now. If you have any questions, I have office hours, so you can stop by. I'll see you guys next time.